In mathematics, the convex hull or convex envelope of a set X of points in the Euclidean plane or Euclidean space is the smallest convex set that contains X. For instance, when X is a bounded subset of the plane, the convex hull may be visualized as the shape enclosed by a rubber band stretched around X. With the latter definition, convex hulls may be extended from Euclidean spaces to arbitrary real vector spaces. They may also be generalized further to oriented matroids. The algorithmic problem of finding the convex hull of a finite set of points in the plane or other low-dimensional Euclidean spaces is one of the fundamental problems of computational geometry. Definitions. A set of points is defined to be convex if it contains the line segments connecting each pair of its points. The convex hull of a given set X may be defined as the minimal convex set containing X, the intersection of all convex sets containing X, the set of all convex combinations of points in X, the union of all simplices with vertices in X. It is not obvious that the first definition makes sense. Why should there exist a unique minimal convex set containing X for every X? However, the second definition, the intersection of all convex sets containing X, is well defined, and it is a subset of every other convex set Y that contains X, because Y is included among the sets being intersected. Thus, it is exactly the unique minimal convex set containing X. Each convex set containing X must contain all convex combinations of points in X. So the set of all convex combinations is contained in the intersection of all convex sets containing X. Conversely, the set of all convex combinations is itself a convex set containing X. So it also contains the intersection of all convex sets containing X, and therefore the sets given by these two definitions must be equal. In fact, according to Carathéodory's theorem, if X is a subset of an n-dimensional vector space, convex combinations of at most n+1 points are sufficient in the definition above. Therefore, the convex hull of a set X of 3 or more points in the plane is the union of all the triangles determined by triples of points from X. And more generally in n-dimensional space, the convex hull is the union of the simplices determined by at most n+1 vertices from X. If the convex hull of X is a closed set, then it is the intersection of all closed half spaces containing X. The hyperplane separation theorem proves that in this case, each point not in the convex hull can be separated from the convex hull by a half space. However, there exist convex sets, and convex hulls of sets, that cannot be represented in this way. One example is an open half space together with a single point on its boundary. More abstractly, the convex hull operator CONV is called a vertexive. In fact, every convex polytopen is the convex hull of its vertices. If the points of are all on a line, the convex hull is the line segment joining the outermost 2 points. When the set is a non-empty finite subset of the plane, we may imagine stretching a rubber band so that it surrounds the entire set and then releasing it, allowing it to contract. When it becomes taut, it encloses the convex hull of. In 2 dimensions, the convex hull is sometimes partitioned into 2 polygonal chains, the upper hull and the lower hull, stretching between the leftmost and rightmost points of the hull. More generally, for points in any dimension in general position, each facet of the convex hull is either oriented upwards or downwards. The union of the upward-facing facets forms a topological disk, the upper hull, and similarly the union of the downward-facing facets forms the lower hull. Computation of convex hulls. Computing the convex hull means constructing an unambiguous, efficient representation of the required convex shape. The complexity of the corresponding algorithms is usually estimated in terms of n, the number of input points, and h, the number of points on the convex hull. For points in 2 and 3 dimensions, output-sensitive algorithms are known that compute the convex hull in time O. For dimensions d higher than 3, the time for computing the convex hull is, matching the worst-case output complexity of the problem. Minkowski addition and convex hulls. The operation of taking convex hulls behaves well with respect to the Minkowski addition of sets. In a real vector space, the Minkowski sum of two sets S1 and S2 is defined to be the set S1 plus S2 formed by the addition of vectors element-wise from the summand sets. S1 plus S2 equals X1 plus X2, X1 S1 and X2 S2. More generally, the Minkowski sum of a finite family of sets Sn is the set formed by element-wise addition of vectors Sn equals Xn, Xn Sn. For all subsets S1 and S2 of a real vector space, the convex hull of their Minkowski sum is the Minkowski sum of their convex hulls. CONV equals CONV plus CONV. This result holds more generally for each finite collection of non-empty sets CONV equals CONV. In other words, the operations of Minkowski summation and of forming convex hulls are commuting operations. These results show that Minkowski addition differs from the union operation of set theory. Indeed, the union of two convex sets need not be convex. The inclusion CONV is generally strict. The convex hull operation is needed for the set of convex sets to form a lattice, in which the join operation is the convex hull of the union of two convex sets CONV equals CONV equals CONV. Relations to other structures. The Delaunay triangulation of a point set and its dual, the Voronoi diagram, are mathematically related to convex hulls. The Delaunay triangulation of a point set in Rn can be viewed as the projection of a convex hull in Rn plus 1. Topologically, the convex hull of an open set is always itself open, and the convex hull of a compact set is always itself compact. However, there exist closed sets for which the convex hull is not closed. For instance, the closed set has the open upper half plane as its convex hull. Applications. The problem of finding convex hulls finds its practical applications in pattern recognition, image processing, statistics, geographic information system, game theory, construction of phrase diagrams, and static code analysis by abstract interpretation. It also serves as a tool, a building block for a number of other computational geometric algorithms such as the rotating calipers method for computing the width and diameter of a point set. The convex hull is commonly known as the minimum convex polygon in ethology, where it is a classic, though perhaps simplistic, approach in estimating an animal's home range based on points where the animal has been observed. Outliers can make the MCP excessively large, which has motivated relaxed approaches that contain only a subset of the observations.